Happy Thursday. Already the weekend. Nice. 75 minutes. First 25 minutes, we're going to continue the review stuff. First thing, let's write this as something greater than or equal to 0. When solving an inequality, first you need to find breakpoints. Remember that? Breakpoints are wherever the expression is 0 or undefined. Well, the expression's a polynomial. Polynomials are defined everywhere. So we just have to solve that for 0. Those would be our breakpoints. Bummer. I don't think that factors by grouping. Which is a shame. That means we need to solve that cubic polynomial. Do you remember the technique for finding the zeros of a polynomial?
You factor out 4x cubed minus 17x squared. We do that separately for the other thing.
So I think you're trying to do factor by grouping, which unfortunately here I don't think is going to work. If it did, then yes, that's exactly what we would do. That'd be the easiest method. So first you have to use the rational roots theorem to list out the possible rational zeros. Factors of the constant divided by factors of the leading coefficient. Those are all the possible rational roots. Factors of 63. One, 3, 21, and 63, I believe. Factors of 4, 1, 2, and 4. Oh boy, that's a lot of possible rational zeros. Then you would use the remainder theorem. Synthetic division with each of those possible rational zeros until you get a remainder of 0. That means that is a 0, and then you can factor it. That would then bring it down to a quadratic at least, which we'd solve from there. Is 1 a 0? No. -1 is not either. Of course not. That'd be too easy. So I'm going to use instructor's prerogative and cheat. Because I'm not testing every single one of those values. Let me say I listed out all my possible rationals and I just guessed 3 is a 0. So I'm going to use the remainder theorem to verify it. Synthetic division. Remember synthetic? -4, -17, -6, 63. List out all the coefficients. In descending order of power. Four drops down. Now just 4 times 3 plus -17 times 3 plus -6 times 3 plus 63. We get a remainder of 0, so 3 is a 0. Which means x minus 3 is a factor. Can you easily factor 4x squared minus 5x minus 21? I don't think so. Means we have to use quadratic formula. -b plus or minus the square root of b squared minus 4ac. Oh, that's going to be fun. 16 times 21. 25 and 336. 361. Square root of 361. 19. Five plus 19 is 24, divided by 8 is 3. Five minus 19 is negative 14 over 8 would be negative 7/4. Two breakpoints, 3 and negative 7/4. And try to list them in ascending order, it makes it easier. Now we set up the test intervals. Take the real number line, all real numbers, and split them at the breakpoints. First breakpoint, negative 7/4. Then we'll continue on until second breakpoint. There are no others, so then we just continue on forever. And write that because that's the factored form. Polynomial. Again, that's going to make it really easy. So x minus 3 squared is always going to be positive. I can ignore that. Pick a test value from each interval and determine the sign. Negative 10 is in the first interval. Negative 10 plus 7/4 is negative. Zero is a nice one. Positive. And 10 will give you positive as well. Look at the inequality. Is the expression going to be positive or negative? So greater than 0 or less than 0? What's the inequality? It's greater than. You take the positive intervals. Can it equal 0? Breakpoints are included. So that's the solution. Simplifying a rational expression. First thing we want to do, completely factor the numerator and the denominator. Here's the denominator. Now the numerator factor. Three x plus 1 times x minus 3. How would that simplify?
You could cancel out the exponent.
And you're left with what?
3x plus 1 over x plus 3.
Is that a true statement? So remember, to be a true statement, it has to always be true.
You can't have a negative x.
Why can't you have a negative x?
No, you can't have any negative 3 as x.
Negative 3? Well, that's true. But you can't have negative
have,
3 on the other side either, so.
You can't have negatives in the denominator. Or zeros in the denominator.
Right. So negative 3, both sides are undefined, so that's fine. That would still be a true statement. What about when x is 3? Left side's undefined, right? What about the right-hand side? It's what, 10 over 6? 5/3? 5/3 is not undefined. That is not a true statement. You have to include that x can't be 3. Then it'd be true. It's something they generally gloss over in algebra. What's the domain?
Real numbers excessive 3 and negative 3.
It's be written that way. Or you can write it in interval notation. Simplifying rationals. When you add fractions, what's the rule?
The same denominator.
What's that denominator called?
Common denominator.
More specifically,
Equivalent fractions. Equivalent.
you don't want just a common denominator, you want a specific common denominator. Least common denominator, the LCD. What is the least common denominator here?
X minus 6 and X plus 2.
What winds up happening is going to multiply every single term by that LCD over the LCD. This is just how I do it. Look at the first term. Look at the denominator. What term is missing from the LCD?
1.
Hmm?
1.
X plus 2. So multiply the numerator by X plus 2. Same thing with the second term. What's missing from the LCD?
X minus 6.
So that's what we multiply by. Third term, what's missing?
Both.
The whole thing. Now it's just a matter of simplifying that. Minus x cubed, they're gone. We're going to have a plus 4x squared plus 2x squared plus 12x plus 3x. Factor out of 3. Two x squared plus 5x minus 6, is that going to factor? Subtraction rate. It does. Oh, wait. No, I did something wrong. 12 minus 1, no. 2 minus 6, no. 6 minus 3, no. No, I don't think that does factor any further. So it is fully simplified. Perfect. So that's the review. At least what we had time for. Now we get to move on to actual calculus. The limit. We begin just by looking at the limit intuitively. We will formally define it a little bit later. Right. So advice on note-taking. Do not write everything word for word. Just write down key concepts. Slides are posted. They post with the videos, so if you miss something, you can always go back and look at it. It's more important just to get the general idea first. So if we have a function that's defined at all values on an open interval containing the point A, with the possible exception of at A itself. So your function doesn't have to be defined at A. If all of the values of your function f approach a real number L as your values of x approach A, then we say that the limit of f of x as x approaches A is L, or f of x approaches L as x approaches A. And it's written that way. There are two things to note. First, x never reaches A. It just gets closer and closer and closer without ever touching it. Second, what f does at A is irrelevant. We don't care. It's how does f behave around the point x equals A. You know what? I'm gonna do Let's call that A. Well, write some function f of x, whatever. There's the point A. That is the line L. How does the function behave around this point? So typically what we do is we draw bands. Pick a different color. This will work. So the idea is now we shrink this band. How's the function behaving as that band shrinks? It approaches that point, which is L. That's the limit. Even if we were undefined, I could have put that as a whole. That's still your limit. Because again, what the function does exactly at that point is irrelevant. It is what is it doing as we approach it.
When you post the slides, are you going to have your annotations on it?
Typically, I don't put them up before, because I wait till I annotate on it and then put it up. We can also have what's known as one-sided limits. So a limit from the left and a limit from the right. And the ideas are generally the same, except if we're coming in from the left, your values of x are less than a. Right? And again, you never actually get to a. And that is how we would write a left-handed limit. Notice the subtle change. All right, so that would be read. Limit of f of x as x approaches a from the left is L. And again, the right-hand limit is practically identical, except now your values of x are going to be larger than a, right? And this is how it would be written. Now it's a plus instead of a minus. And that would be read, the limit of f of x as x approaches a from the right is L. Existence of a limit. A limit exists if and only if your two one-sided limits are the same. So if you have both the left-handed and right-handed limit being L, then your limit is L. Yeah, it makes sense. If your function behaves differently on either side of A, then clearly it's not really converging to one value, right? If you once again draw that little band around A, shrink that band, is it going to a single value? It goes to two different values. So it doesn't behave the same, so there can't be a limit. That's why your limits, your two one-sided limits have to be identical. There is another possibility, though. So let me draw it here. Now what I'll do is this. Is there any one value that the function seems to be going to?
Shouldn't that be an infinite number? There's a squeeze theorem.
I haven't gotten to the squeeze theorem yet. Squeeze theorem doesn't really work with infinite, though. It squeezes it to some specific value, a finite value. So this limit actually doesn't exist, but it's a special type of not existing. We say that that function is increasing without bound on either side. Right, specifically now from the left, it's increasing without bound, so it's an infinite limit from the left. Let f of x be a function defined at all values in some open interval b to a. If they increase without bound, then the limit we say is positive infinity, and it is written that way. Again, it's important to note that while we are saying the limit equals infinity, technically the limit just does not exist. What is infinity? That's the correct answer. Who knows? It's just a concept that we came up with to mean there's no upper limit. There's no upper bound. I didn't have to do that. I'll change it later. If instead the values are decreasing without bound, then we say the limit is approaching negative infinity, right? And it'll just be written that way. Again, that limit does not exist. This is just a representation to tell us how the function is behaving. And you have similar definitions for limits from the right. All right, increases without bound as we approach a from the right. We say it's positive infinity. Decreases without bound as we approach a from the right. We say the limit is negative infinity. And if both one-sided limits go to positive infinity or negative infinity, then we just say the limit as x approaches a is either plus or minus infinity. So it'll be the same thing. Your two one-sided limits have to do the exact same thing in order for the limit to exist at that point. So positive infinity, and there's your negative infinity. What is a vertical asymptote? It's a vertical asymptote, right? How was it defined in pre-calculus?
The y value to the x is never crossed.
Maybe the y values for the x never cross.
Not the things never cross, like they can't go over the vertical asymptote. It's the line they approach.
Be careful. It's still a vertical asymptote. And it touches it. But I do agree with not crossing it. Can't cross it. They didn't really give you a definition in pre-calc. They kind of just showed you what it is. Now we can define it. Because you kind of keyed in on what the definition is. Because you said approaches. Now what should you think of when you think of approaching a limit? So f of x be a function if any of the following conditions hold, then that line x equals a is a vertical asymptote of f of x. Limit as x approaches a from the left of f x is either plus or minus infinity. Limit as x approaches a from the right is plus or minus infinity. Or the limit as x approaches a is plus or minus infinity. Okay. As the example here shows, only one side has to be plus or minus infinity to be a vertical asymptote. From the right, the limit's not infinite. It is some specific value. But from the left, it's positive infinity. So it's an asymptote. There was another asymptote you looked at in pre-calc, wasn't there? Technically two. Horizontal, right? We'll define that later. And then there's also a slant. You should have studied slant or oblique. Yeah, we just don't define that one. That's actually a pretty hideous definition. Slant asymptote is in a category called curvilinear asymptotes, which we generally ignore. You're going to numerically approximate this limit. Oh, it's piecewise too. So we should have two functions I want to look at. One less than or equal to 2, one greater than 2. For purposes of this exercise, I'm going to define two separate functions. I can define it as a piecewise, but for this exercise, it's going to be better to define it as two separate. So let's call FL, or I could go lower f, larger f, F1. Well, it doesn't matter, actually. I think I like F1 better. Notice it's in brackets, and I have an underscore after the x. That underscore is specifically telling Mathematica that x is an independent variable. And it was x plus 2. And of course, Mathematica is now color-coded, which is nice. The independent variable is green. If it's not green, then your syntax is off. The colon equals specifically says it's a definition, it's defining it. You don't want it to be equal. And I'll define my lower function now. Which was 3x minus 5. I'm just going to go ahead and execute that right now. So to execute, you don't hit enter. If I hit enter, it just moves me down to the next line. Shift enter, executes. Or if you hit enter on the numerical pad of a keyboard, same thing. That's shift enter. So now they're stored. I'm going to create a table of values. I can also leave comments. So anything between parentheses star is a comment. It will not read it as executable code. Right, really great if you're writing a long code. Put a comment with each step to remind you what you're doing, or if you're sharing with someone, they know what you're doing. It's great for that. You can also use Mathematica as a word processor. For now, I'm just going to move down to the next line. See that plus? That's very, very dim on the screen apparently, but there's a plus sign here. You scroll over, it says, it's not going to show, but it says choose new cell type. If you hit it, it's not going to show. I have to move my screen over for now, which is truly annoying. Plain text. It's not code, it is just plain text. There are palettes in here as well that let you enter mathematical formulas. Palettes. There's a whole bunch of them. Also do, if I just type other style, the drop down, it gives you a whole bunch of options. So it's more than just mathematical evaluation. So if you don't like Word, you can use Mathematica to type up your projects. Which might be easier if you want to incorporate your code into the actual text of the project itself. So I'm going to create a table of values. I want two values, an x and then f of x. I need the variable for the table. My table variable is x. A list of values for x. Several ways. I'm just going to list out several values. Some more braces. Oh, wait, actually, I don't want f. I'm doing left-handed limit, so I want less than 2. I want f1. There you go. That's better. So we're approaching 2 from the left. A value of x close to 2 but smaller than it. .9. Let's get closer. Let's get closer. Let's get closer. I can adjust it if I'm going to need more values later. Shift enter. So this is the default output of a table. I don't like it. If I use the table form command, that's better. However, it's not giving me any kind of headings. if I just put the table within the actual table form command itself, I can add table headings. First set of braces is going to give you headings for each row. I don't really need them for rows, so I leave it blank. Now headings for columns. Anything you put in quotation marks, Mathematica will read as a string. Oh, how dare he use programming jargon. Essentially just plain text. Our first column was X, right? And the second column represented f of x. That looks much more presentable. Was that enough? Do you get an idea of what f of x is doing from the left? What does it appear to be approaching? 4. Keep in mind, you cannot say that the limit is 4. We'd have to get infinitely close in order to definitely guarantee that. So this is just an approximation. It appears to be 4. In fact, it actually is 4. But we'll learn that later. We'll see how to do that later. So I'm going to take you, I'm going to copy, put you in here. No, I'm not, because I'm going to put you as a picture. Of course I am. Can I convert you by any chance? No, I can't. Oh, that's a bummer. I was hoping I could convert it to an image. But it doesn't look like it's going to let me do it. Ooh, it is. I wonder if that'll work. Let me check. Yes! So you probably couldn't see what I just did. See, but off to the right, you should see nesting bars. Click it, it highlights it. So I'm highlighting that output. Right click, convert to bitmap. That now lets me copy it as an image for easier pasting. So just paste it right into the slides. I'm not going to worry about the writing out what the left-handed limit is. Now we look at the right-handed limit. So what is it doing as we come in from the right? Well, for that, I need to use F2. So values close to 2, but larger. 2.1's pretty close, and it's larger than 2. But I can get closer. Closer. There is actually no rule on how to pick your values. As long as you pick values close to 2, but larger than it, and you get enough to give you an idea of what the function is doing, that's fine. Is that enough to tell us what it's doing? What does it appear to be doing?
Approaching 1.
Appears to be approaching 1. Is it approaching a single value? No, limit does not exist. So we write DNA does not. Right, that is clear from the table. Is that the time already? Crap. Time flies when you're having fun. Questions? We pick up here on Monday. And don't forget to scan out before you leave.